Hello, welcome back to another Godot video. My name is Dan, and believe it or not, yes, this is the next part in my drum machine video. So in previous parts, if you've seen it all, I've been really trying to find a stable clock source, or what could possibly provide a stable clock within Godot. And I really, I tried a bunch of different methods. And let me just describe them a little bit. User Cybereality on the Godot forums was able to come up with a really cool sort of comparative method. And that was one method that I used. I changed it up a little bit with an if instead of because I use a while statement. And I tried it with an if. At the time, I didn't really understand it when I ran these tests, but I think I have a really good idea of how it works this time. And then also the physics modulus, I'm calling it. It basically uses the physics engine. And within the physics engine, and I'll show you this actually really quickly. For this method to work, under project, you need to have your physics engine set to a certain number. Here I have it set to 100. That's what I did the math with. You could set it to something else. The number, there's a limit on this, and I believe it's between 400 and 500 that Godot will just not go beyond. And it makes sense, for the purposes of what Godot usually does, that is the limit. So those are pretty much the 2.5 methods, this I would call like a half method, that I found that actually work. I did also try the OS timer version, and then so I did one direct with a direct, just basically feeding the number 250 into the number of milliseconds that it would delay each beat to get a tempo of 120 BPM. And then I did one with a variable where it had to look at a variable within a formula to get the BPM or get the right delay value. Now, I want to stress that these two methods, the two ones that use the OS timer, destabilize the Godot engine. When you press play on the program, everything freezes. It still runs the code, but it becomes unresponsive. So I was able to get a recording. So I kind of wanted to take measurements down on that. So essentially what I did was I recorded the sound, and then I brought them into my DAW, and then I took readings of where they fell as far as milliseconds go within each beat, and I compared them with theoretical. So before we go over these things, I'm going to do a quick just edit in a video of I brought them into the DAW, then I opened up a drum machine that had the same sound loaded into it, the same hi-hat sound, and I played it against what would be pretty much the theoretical, which is basically it's just MIDI playing back, triggering the drum machine. So here's the results, the audio results of each one. Okay, so as you heard, each one, none of them were perfect, and each of them had like a sort of different degree of accuracy compared to what would be the theoretical. So anyway, as you can see my measurements here, I only did 4 measures of each at first. And I also did the timer module, which uses a timer node for delay, similar to the OS timer, but with a timer node within Godot. And the sound coming from that, it got too off to even give us measurable information. So I omitted that from this. And as we can see, we got a delta. And then over here, what I did, so I took the average of each delta from the theoretical, and I subtracted it to get sort of these weighted results. The reason I did this was that they would center around 0. And so these are the weighted results for that. And within there, these weren't really super telling numbers, but I got them at first. I was just looking for ways to get some readings. And then the min and max for each one. These are basically just the maximum deviation from the theoretical and the minimum deviation from the theoretical. And as we can see, in this particular test, the physics modulus method worked the best, but not by much, only by 3 milliseconds smaller than the OS direct and cyber weighted. So here I took the absolute value of these weighted deltas, and that gave me the average deviation of each. And as we can see, once again, physics modulus was the best in this particular test. I did a little bit of extra analysis over here, and we'll look at this graph really quick. Basically, each point shows how many, everything below the line for each of these is the number of readings that were below the millisecond value. So OS Direct was the only one that had a reading that was at 0 actually. So it had one below 1. And then as we keep on going, we see that the number of data points that are below a certain millisecond deviation, it goes up, obviously. And surprisingly, the first one to hit all of them, or not surprisingly, because Physics Module did the best, surprisingly, it was better than OS Direct. But OS Direct was a close second, along with, what was it? The Cyber method. And for some reason, the one with the if statement, where I just changed Cyber's while statement to an if, did the worst. And then the OS variable did not do well at all. And actually, it did kind of the worst as far as having the fewest ones that deviated at a small level, as we can see right here. So it's interesting, but this is a small data pool. So I actually went ahead and did it again. Oh, actually, before I go into that, I wanted to see, because the OS Direct sounded pretty good to me. I couldn't, when I would listen to it on its own, it sounded better. And I think this is why. These, again, are just the weighted values and not the absolute weighted deltas from theoretical. And what I did was I took the difference between, so basically these differences are the first data point delta minus the second data point delta, and then the second minus the third, so on and so forth. And then I took the absolute values of those and averaged those. So this was basically telling us how big the deviations from beat to beat, from note to note are. And as we can see, the physics modulus and the cyber weighted did pretty well, and they did exactly the same. OS Direct, and I guess just this was why it sounded smoother, was because from note to note, the deviations were less. So it had the best score here. The lower the score, obviously, the better. And the OS variable also was pretty good. It was pretty close to what these did, and then the cyber weighted did the worst here. And that probably is because using an if statement instead of a while loop is just not the way to go. So I did this again, and I did it with 129 data points. This is 16 measures worth of data points. And I gave the timer node another try. I gave it a chance. But again, it was just not doing it. I also tried the OS variable again, but that didn't do it. So basically, I only have readings for 3 here that are worth it. And the OS direct, the OS timer, got way off. So like it got basically, this is telling me that any timer method is really not the way to go, because it has no tie-in. Especially if these are the deviations in milliseconds, and we see that the center, like basically all of these are supposed to center around 0, or at least have 0 as a data point throughout, or close to 0, or both negative and positive results. So it's hitting both too early and too late. And here the deviations continued, but they kind of fell ahead. It got ahead of where it needed to be. And for that reason, at this point over here, these are just here. These average columns are just here for quick math using the spreadsheet. But anyway, I took this out of the readings from here on, and was just focused in on the cyber method and the physics method. So again, these are the weighted values, the weighted differentials right here. And somehow they both came out to integers, which was interesting. And then I did actually do the differentials for the OS as well, but I took it out after this step. So anyway, this was all just doing math up here. Let's go down to where I have some interesting results at the bottom, and I have them labeled, luckily. So the smoothness index that we looked at, they're practically, this is the OS right here. And for some reason it just didn't perform as well on that. And my guess is that it's because the deviation went off. I didn't do anything to correct that it at some point had a hiccup and that threw off values. But it did still sound pretty all right. It could have also had something to do with the performance of my computer. I did it later in the day. I'd been running a lot of things like OBS and my DAW on and off. So I probably should have restarted before doing this test. But anyway, this is what I got. And this is, it's real world application. I'm not going for super science, super controlled results here. So anyway, this is the comparative method. And then this is the one based off of a physics modulus. And they're pretty close. This is very, very close. They're within 1 millisecond of each other. And let's see, average deviation I only did for the two. Again, within a millisecond of each other. Within 0.4 milliseconds of each other, so less than half a millisecond. Very close. Again, this is the comparative Cyberealities method, and this is just the physics modulus method. We can see the range again. Cybereality did well. The range here, not as good for the physics modulus, and then of course the range for the OS was inflated. So finally, I just took both the deviations for Cyber's method and the physics method and basically did the same thing as that chart that I did here, but I haven't made a chart yet. I don't think I really need to. But anyway, this shows how many of the results were below 1 millisecond. Cyberealities had 8, and the physics one was 11, which is very good. Within 2 milliseconds, you can see Cyberealities has more, but only 1 more. And then, again, Cybereality again by 1. Here we see Cyberealities got ahead by 9. And then, again, it's still ahead, but by less. And then the physics catches up. So anyway, it's just interesting. Here we see at 10 milliseconds, the physics model is ahead. And all the way up to 20 milliseconds. At 20 milliseconds, all of the samples were done. The Cyber's comparative method got them all at 19 milliseconds, and then the physics one came through at the finish line at 20 milliseconds. So 1 millisecond's difference. So basically, this is telling me that essentially they're the same. I'm not going to do much more testing here. I might do one larger thing just to finally put it to bed. But for my drum machine, I think I'd like to have multiple clocks. I'd like to have the original timer node based one, because having an odd bird, having a weird clock, sometimes that could add some real vibe to a sound. You know, having an unstable clock. It's similar to, like, let's say you have an analog sequencer that's controlling your synthesizer or triggering your drum machine. It's something interesting. It has deviations from a perfect, very close, accurate computer clock. And then these physics ones, or Cybereality's one, is closer, but it's not perfect. But for my drum machine, I do want an option for it to be very, very close, so it could be used with other things, used with other applications, and have a steady clock. And so my next step is to go into the C++ library, sort of bring that in. You can use C++ codes or C++ libraries within your Godot project. And I've looked into that a little bit, and I don't think it's going to be too difficult for me to make the audio engine run in C++. I found some really good tutorials, walkthroughs, and I will mention them when I actually start doing it in my next video for the drum machine. I'm not sure exactly when I'm going to get to it. I have a full-time job, so it may be a few days, hopefully not more than a few days, before I get to it. Thanks to everyone who's been commenting on the videos, and also thanks to Cybereality and everyone on the Godot forums for the support and the playing along with me on this sort of project. It's been really helpful, and I'm excited to learn how to integrate C++ functionality within Godot, and hopefully that can get us a real steady, accurate clock. Thanks for watching. Have a good day.